Assalamu alaikum. In today's lecture, we shall talk about three very important laws which govern the working of electrical machines. We start with the Faraday's law. Faraday's law states that when flux passes through a turn of wire, it induces a voltage in it, and the induced voltage is proportional to the rate of change of flux. That is, if you have a core of ferromagnetic material and some flux is passing through it, this flux passing through it may be due to some source of MMF connected to this core, and if you have a wire wound on it, then this flux passes through this turn of coil. If there were a single turn of coil, then induced voltage is given by the induced voltage is equal to rate of change of flux. And if there are multiple turns, then induced voltage is given by number of turns multiplied by rate of change of flux. Here, this negative sign is due to Lenz's law. So Lenz's law states that the polarity of the induced voltage will be such that it will oppose the cause producing it. What does it mean? It means that if we short circuit this coil, then due to induced voltage, current will flow in this coil, and the direction of current will be such that the flux produced due to current in this wire will oppose the actual flux which is producing it. That is, in this actual the direction of this flux phi is upwards, and if current flows in this coil, then this due to current in this coil, flux will be produced by this coil, and the direction of the produced flux will be downwards. That is, the direction of current will be indicated by the fingers. This will be the direction of current in the coil. So Lenz's law states that the direction of induced voltage will be such that it will oppose the cause producing it. The cause which is producing it is this flux. So due to current in this coil, another flux will be produced which will oppose this flux. So the flux due to the current in this coil will be downward. That is, the direction of current will be indicated by these fingers, that is towards right. This will be the direction of the current in the coil. That is, the polarity of voltage will be this one, polarity of induced voltage. You know that for a voltage source, if this is the polarity, then current leaves the positive end. So current will leave the positive end. In this expression, we have assumed that the same flux passes through all these turns of wire. However, there may be leakage flux. Due to leakage flux, different coils will have different flux lines passing through it. So in that case, the total induced voltage, if there is leakage flux, then induced voltage will be equal to sum of voltages induced in each individual coil, EI. EI is the voltage induced in ith turn of wire, and where EI is equal to its magnitude is equal to d phi I by dt, where phi I is the flux linking with the ith turn of the wire. This is equal to, therefore, is equal to d phi I by dt. E induced in ith turn of wire is d phi I by dt. So this EI is replaced over here. We know that this summation and differentiation, these can be interchangeably written. That is, this is equal to d by dt and sum of flux linking with each coil, each turn of the wire. This sum is called flux linkage, denoted by lambda. Lambda is equal to sum of flux linking with each individual coil. With this definition of flux linkage, the total induced voltage is also equal to d lambda by dt, where lambda is the flux linkage. With this description, now we are also able to talk about the eddy currents that we discussed in the last lecture. What we can see is that this conductor, this core, may also be a conducting material. That is, this flux not only links with the turns of the coils, but also links with the core itself. Therefore, this flux will also induce voltage in the conductor itself. So let's talk about the eddy currents. So this flux not only links with this coil, turn of wire, but also links with the ferromagnetic core itself. And this ferromagnetic core, this may also be a conducting material, and therefore this changing flux will also induce voltage in the core itself. And due to induced voltage in the core, current will start flowing in the core itself. And you know that current flowing through a resistor, there are I square R losses. So these eddy currents, which are produced in the core due to changing flux, these result into losses. These losses are not only wasteful of energy, but may also result into heating of this core, which is undesirable. So to further clarify it, let me sketch the top view of this core. Here is the top view of the core, looking the core from the up direction, and flux in this case can be denoted by a dot notation if we look it from the top. And due to this changing flux, this is the direction of flux is outward, and due to this changing flux, voltage will be induced in this core. What will be the polarity of the induced voltage can be determined by the Lenz law. That is, the polarity of induced voltage will be such that it will oppose the cause producing it. The cause producing this voltage is this flux, which is outwards, and the induced voltage will be such that if the current flows due to induced voltage, flux that will be produced due to that current will be into the surface upward. That is, the direction of current will be in the clockwise direction. So these eddy currents will start flowing in the core of the conductor. If we are looking from the top of this ferromagnetic material, so this will be the direction of current in the core. So how to reduce these losses? We can see that these losses are dependent upon the resistance. If we can somehow reduce the resistance, we will be able to reduce these losses. And we also know that resistance is dependent upon the length of the path. So if we can somehow reduce the length of the path followed by these currents, the resistance encountered will be reduced, and hence the losses will be reduced. So what do you think can be a strategy to reduce the length of the path followed by the current. An approach that is utilized in electrical machines is to laminate the core. That is, instead of using this solid core, what we do is we make the core out of small strips. That is, if we have a rectangular core, we will not use a solid rectangular core. Rather, we shall use small strips, thin strips of core. Each strip is electrically isolated from each other, and due to this, the current flowing, because the eddy current which is flowing will be limited in each of this lamination. The path length will be reduced, and hence resistance will be reduced, and therefore eddy currents will be, these losses due to eddy currents will be reduced. So therefore all electrical machines are laminated. Here I have an induction motor, and you can see the core of this induction motor is laminated. Maybe these laminations are not quite visible over here. I have a small transformer, small electronic transformer for electronic circuits. You can see that the core is made up of small thin strips, and these strips are to minimize the eddy current losses. Each strip is electrically isolated from the other strip, and thinner are the strips, smaller will be losses. So to minimize the losses, these strips should be as thin as possible. However, this will increase the engineering cost, and hence there is always a compromise between the cost and the energy losses due to eddy currents. Let's take one example. We have this ferromagnetic core, and in this core this flux phi is flowing in this direction. This flux may be due to some other winding, for example over here, through which current is flowing, for example this winding, and due to current in these windings this flux is flowing. This flux is given by this much flux is flowing in the core, and we want to determine the voltage induced over here, this induced voltage. We know that induced voltage is equal to minus n d phi by dt. This negative sign only tells us about the polarity, and n is the number of turns that is also provided to us. There are 100 turns over here, and then magnitude of induced voltage is equal to 100 multiplied by d by dt of 0.05 sine of 377 t, which comes out to be equal to 1885 cosine of 377 t, which is the same as 1885 into sine of 377 t plus 90 degrees volts. Polarity of this induced voltage can also be determined. The direction of flux is this one, and polarity of this voltage will be such that if this is short circuited, current will flow such that the flux produced by current in this wire will oppose this flux. That is, the direction of flux due to current in this coil will be downwards, and therefore the direction of current will be this one. That is, this is the positive end of the voltage source.